Hello and welcome back. This is 9.2. We're picking up with hypothesis testing, steps 2, 3, and 4. So 9.1 was all about forming hypotheses. Now we're going to follow through. Step 2 is the most complicated. Step 3 and 4 really just kind of flow from step 2. At the end of this, you should be able to do both of these things, and these are the same ones that were in 9.1. Okay, so step two. The first thing step two talks about, and this is the sub step that Top Hat has. Remember, I lumped a bunch together into my step two, is determining what test is appropriate. And with hypothesis testing, the main steps, 1, 2, 3, and 4, are all the same. They change slightly from test to test. But basically, the statistical test depends on the situation. And if you look forward in Top Hat, in the textbook, right, we're starting into the different chapters, and they say t-test for this, or analysis of variance, or chi-square. Each one of those is a different statistical test. The type of test that we use depends upon the situation. Right? This is part of what we're going to learn as we go forward, learning the different tests. For now, it's always based upon what we know. And here we know mu and sigma. We know everything there is to know about a reference population. So that means we can find the probability of the outcome, the sample mean, using the central limit theorem and z-scores. This is why chapter 6 was important. Right? When we know a reference population, we can use that information to find the probability of a sample mean. So this test, the one's appropriate for the example we're talking about, is called the z-test. The z-test we'll talk about in the next set of slides, which is chapter 10. All right, once we figured out that it's a z-test, that sets us up for determining the rejection region. We can look at the outcome. We're going to turn the outcome into a z-score and think about what that z-score tells us, whether we have a common outcome or an uncommon outcome. The rejection region here is going to be set up in terms of the z-scores. And to do the rejection region, we start with the assumption the HO is true. We're assuming the null hypothesis is true. Because if we assume the null hypothesis is true, then we kind of have a sense for what's common and uncommon. Right? We use the null hypothesis to figure out how to judge the experience. So think about going to a new restaurant. Right? If we go to a new restaurant, the null hypothesis is that the new restaurant's no different from all the other restaurants that we go to. There's going to be people there that are friendly. The food will be good. Oh, there's a phone call. The food will be good. Okay, sorry about that. The null hypothesis tells us, right, what to expect. We assume it's true. We know what to expect. We also know what's unlikely. If the restaurant is not like the ones we're used to, then there'll be rats. The food will be nasty, and it'll be dirty. Right? So if we assume the null hypothesis is true, it gives us some basis for making expectations. For the marijuana example, right? If we assume that the people who smoke marijuana have no difference in their memory abilities, then the null hypothesis tells us what to expect for the population mean. It should be not different and be 75. Right? It also tells us what to not expect. It tells us that we should not expect the population mean of the marijuana smokers to be way less than 75 if it's true. Right? If it's true, we should get something close to 75. The rejection region, right, is where we consider what's unlikely. Right? So we use this is the standard for what's unlikely. It tells us where the things not consistent with the alternative, with the null hypothesis, can be found. part of what we need to consider is what we call the significance level of the hypothesis test. And this is represented by alpha. Alpha there in parentheses looks like a fish, is the first letter of the Greek alphabet. And we use alpha to represent the significance level. Alpha, there's two standards of what's unlikely in hypothesis testing. One is 0.05 or one is 0.01. Alpha of 0.05 means that according to the null hypothesis, right, if we assume the null hypothesis is true, there's a 5% chance of being that low. Right? For the restaurant example, let me put that in an example, right? If we use a significance level of 0.05, would be, we're saying that, right, there might be a 5% chance, given what we know about restaurants, there's a 5% chance it's going to have rats. If it's 0.01, right, then it's a smaller probability, right? So we say what's unlikely is 1%. Those are proportions, 0.05 or 0.01. And those are standard. Every hypothesis test uses one or the other. Most people, you will use 0.05, but sometimes we'll use 0.01. We'll talk about that later on. So to set up the rejection region, right, the conditions in which we define likely and unlikely events for a hypothesis test, we need to consider the type of alternative, right, the sign in H1, as well as the level of significance. And this will give us the critical value that marks the boundary, tells us exactly where the rejection region begins. A score that falls into this area is considered unlikely to have occurred if the null hypothesis is true. Right? By our definition, by our level of significance definition, it is unlikely. So why do we say rejection region? I like to think of this visually, right? So here is a normal curve. Right? After all, this is a z-test. We're working with z-scores. So here's a distribution of z-scores. Right? I call it the rejection region because to me, I think of it for mathematicians, they say, they think about number lines and areas and things, but I like to see the areas. I like to experience it. So let me just get me the pen here. Where'd it go? What's the cursor? There it is. Let's think of our situation. You'll see why we call it the rejection region. Two things to worry about when we find a rejection region. One is the level of significance, and let's say, for example, it's 0.05 for this one. We chose that. That's under our control. The other thing is the alternative hypothesis, the one we worked with, had a less than because the researcher we're reading about wants to see if marijuana users have a memory impairment. Well, let's start with this. Put the sign right above. Which way does that point? Right? That less than points over here. That tells me the things that are unlikely given the null hypothesis of no difference, right? If there's no difference, that's where we get this curve from. If there's no difference, we should see a mean of 75, which is a z-score of 0, right? We should see things here in the middle. Things that are unlikely in the direction that the researcher thinks are going to be at the lower end. Here's where their memory performance is so bad, it's unlikely given the null hypothesis. The null hypothesis gives us this whole curve. The rejection region considers the alternative and the level of significance to say this area right here, anything that would fall in this area, the rejection region is from this boundary on down. There's the rejection region. R. Anything that's here we call the rejection region. Because here's, by definition, here's the things that are unlikely given the hypothesis of no difference. Okay, does that make sense? All right, let me just get to the pointer. Let me change my color. Let's go with purple. Here we go. Now, what if the level of significance was 0.01? Right? Well, with the same alternative, 0.01 is going to be down here. I'll color in this little bit, right? Because 0.01 is a smaller probability. If we use 0.01, we're saying really unlikely, right? So the rejection region is going to be a smaller part of the curve. When we think of these as proportions, you think of these as areas, right? So 0.01 is a smaller part of the curve compared to 0.05. But in both cases, the rejection region defines the outcomes, the sample means, the z-scores that are not likely given the null hypothesis. They're not likely if we pretend the null hypothesis is really true. Let's consider another example. All right, here I've got, I got the purple, so I'll stick with the purple. Let's say, again, we have alpha's 0.01. I'll stick with purple. Level significance 0.01. And this time, let's consider the other variety of directional hypothesis. What if it was a greater than? Well, greater than alternative, it points over to this end. And if for some reason we thought marijuana significantly improved people's memory, which it does not, we would expect an outcome in the higher tail, no pun intended, according to what the researcher thinks. Right? According to the null hypothesis, here's what we should expect here in the middle. Right? The things inconsistent with that are up here. Right? So here's the rejection region for greater than alpha 0.01. Now, while I changed my color, where is the rejection region if alpha is 0.05? Let's go back to red for 0.05. If alpha were 0.05, I did the zero. I forgot the zero again. If alpha is 0.05, where am I going to draw the boundary? Over here or over here? 0.05 is a bigger slice of the curve, so it's going to be here, inbound, towards the center of 0.01. Here's 0.05. Right? The rejection region for 0.05 is always bigger. It always includes the rejection region for 0.01. So really this whole thing is the rejection region for 0.05. It's in the upper tail because that's what we expect, or where we would expect things according to the alternative if we have a greater than. It gets a bit more complicated when we have a non-directional hypothesis. Non-directional hypothesis is it does not equal. The H1 does not equal. And this is where we just had a difference. If they're just looking for a difference, right, we don't know then if it's less than or greater than, right? Less does not equal really means less than or greater than. Notice then, right, both of these signs were pointing to both tails. So the rejection region's labeled here on this chart and is marked out in blue, right? It's alright, just lost my train of thought. Happens sitting in my house just as it does in front of you guys in the classroom on the board. The rejection region gets split in two. Now the funny thing about the rejection region is, right, the blue parts at both ends have to equal alpha. The level of significance is, again, another situation where it's the Price is Right rule, right? You cannot go over the level of significance. So if alpha is 0.05, right, in this case, 0.05, that means 0.025 is in this tail, and 0.025% proportion of the total is in this tail. In the total, it's 5% of the entire curve, but we split that 5% into 2.5% down here, 2.5% up down here. Right? The rejection region is the same size as alpha 0.05 directional, but here it's just split in the two ends. Now you can kind of see here it says critical value. Critical value is the boundary, is the number that marks off that particular boundary. And this is exactly what we did in the end of chapter 6. Remember we had the z-table and we said what's the z-score that marks off a certain area? That's exactly the problem we have here. Here we want the critical value that marks off 0.025 in the tail, right, beyond. Or it's the same one over here, 0.025 in the tail. Right, that would be the critical value. For the directional test, we could go back. Right, there's a critical value. We can find the z-score that corresponds to that boundary. We can find the z-score that corresponds to that boundary. I found them for you. Here they are. Now you can verify this for me, right? If you go into the table, it's probably a good exercise to do. Go into the standard normal table. look for 0.05 in the entry, right? 0.05 to the left in the tail. So you go to the negative z-score table, look for 0.05 to the left, and when you find it, right, you should find 1.65, negative 1.65 as the entry. Negative 1.65 is the z-score that marks off 0.05, right? So if I were to draw a normal curve, right, there it is. 5% is here, 0.05, and what do we have up here would be 0.95, and this critical value, the z-score, is a negative 1.65. That's the case, right, if we have a less than in the directional alternative, an alpha 0.05. If we have a positive, a greater than, we use the positive value, right? Remember, the curve is symmetric. Whatever's true of the lower tail is also true of the upper tail. So the critical values for z when it's a directional test, right, is negative 1.65 for less than 0.05, right? Positive 1.65 for greater than 0.05. Notice, right, we're never going to use both of these. We're never going to use more than one cell in this table because we're only ever going to have a directional hypothesis or a non-directional hypothesis. We're only ever going to have 0.05 or 0.01. We're never going to have both. Alpha 0.05 two-tailed, these are the critical values, and this is what happens if we have it does not equal, right? We'd use both of those as critical values. Down here, if alpha is 0.01, the critical value becomes negative 2.33 for less than, positive 2.33 for greater than, right? And then here's the non-directional 0.01. This is something, you don't have to memorize these. Remember, you get to use a formula page on the exam, right? So these will be available to you on the exam. But you should understand now where these are coming from. This is exactly what we did at the end of chapter 6. We know the areas of the curve. That's a level of significance, right? And we just need to find the scores that mark off the different areas, right? This is 0.05 in to the left of the z-score. This one is actually 0.025 to the left of the z-score because it's alpha divided by 2. Right, so I'm going to go over the non-directional ones just one more time, right? Non-directional, right, is there. So if alpha is 0.05, right, that means 0.025 in the upper tail as well as 0.025 in the lower tail. And here's where you can look it up. If you look up 0.025 in the standard normal table, right, 0.025 to the left and then find the z-score that marks it off, you will see a negative 1.96. Because it's symmetric, then this critical value is the same magnitude but positive, 1.96. Right, alpha is split in two, but there's the rejection regions kind of colored in. So that's this rejection region. The third step in hypothesis testing is doing the actual statistical test. This is where we would use the central limit theorem and get the z-score, just like we did at the end of chapter 6. But we're going to put this on hold and talk about it more when we talk about chapter 10. We talk about t-test. This is going to be different. We'll have a different test to throw in this stage. All right, let's go to step 4 then. Step 4 is putting it all together, making a decision and stating a conclusion, right? Step 4 relies on the previous steps, right? Hypothesis testing, theoretically, how it works out, right? If I have an honors student, I'm going to ask my honors student to form her hypotheses and set up her rejection regions before she collects any data at all, because those things are based on logic. Then the third step, she does her experiment, right? Gets her outcome, does a t-test, gets the statistics, the sample means. Now in step 4, we're going to put it all together. We look at the outcome and use and apply our decision criteria. So the first thing is the decision. Is the outcome in the rejection region? Now for the test we're talking about, the outcome is going to be a z-score. We're going to turn the sample mean that was in that problem into a z-score and then compare that z-score to the critical value. Right? Is it in the rejection region? So let me right come up with a quickie. Right, here's what we had, something like this: alpha 0.05. Here's the right alpha 0.05, and we had a right less than in the alternative, so the critical value is a negative 1.65. If we get a z-score that is less than or equal to negative 1.65, right, it's in the rejection region. We can compare the obtained value of z, what we get from step 3, to the critical value that we found in step 2. Right? So the rejection rule is we reject the null hypothesis. Right? We're going to say the evidence we have is inconsistent with our belief if we find an extreme outcome. An extreme outcome is a z-score that we obtain, z-score OPT is a subscript. If the z-score we find in step 3 is less than or equal to negative 1.65. Right? So if it is in the rejection region, if it is less than or equal to negative 1.65, we reject the null hypothesis. If it's not, we fail to reject the null hypothesis. So here the rejection region is what is in red. I'm going to write that in there. And then the other part is fail to reject. I'll make that green. Right? Anything over here, we fail to reject the null hypothesis, FTR. The rejection region sets all possible outcomes, any z-score we could get, into two areas, the rejection region and the fail to reject region. We look at this number 3, map it onto our chart, and we know what our decision is. Either we reject or fail to reject the null hypothesis. Notice what this says, right? If we reject the null hypothesis, we're saying our assumption is not true. If we fail to reject it, we're saying we have no evidence our assumption is not true. The conclusion, right? So here's the other chart. This is for a two-tailed test before we get to the conclusion, right? Is the outcome in the rejection region? If it is, right, here's the rejection region, right? So here, any outcome that is less than or equal to this critical value, or something greater than or equal to this critical value, here it is, this critical value. So the rejection region, the rejection rule has to be stated two ways. In this case, we reject the null hypothesis if it is less than or equal to this critical value, or if it's greater than or equal to that critical value. Notice that it's an or, right? It's not an and. We only have one outcome. It will be here, or it will be here, or it will be in the middle, which is the fail to reject region. Two-tailed hypothesis tests are interesting. We are looking for a difference. We don't know what's happening going in, but coming out, we know. Right? If we do this hypothesis test and our marijuana group scores up here, right, we would have evidence they're different, and we also have evidence that they're better. How do I know they're better? They scored higher than we would expect, right? They're in the upper tail. So we didn't know anything about directionality coming in, but once we do the test, we can make a statement of direction. The conclusion. The conclusion takes the logical decision and applies it back to the data. If we reject the null hypothesis, we have evidence in favor of the alternative. So we would state the alternative, right? In the example I have, if we reject the null hypothesis that the marijuana users are not different, then we're saying that they are different, and we might have evidence then that they scored lower on the memory test. If we fail to reject H1, sorry, that parentheses should be a 1. If we fail to reject the alternative, I'm sorry, that should be a 0. Let me write that in. Sorry, that's a typo. I hit the wrong key. If we fail to reject the null hypothesis, then we have no evidence in favor of H1. Notice that, right, the difference in wording. The word no here is missing up there. We add the word no if we fail to reject. If we fail to reject the null hypothesis, we have no evidence in favor of the alternative. If we fail to reject, we're saying, right, we're seeing what we would expect. That's actually kind of boring, right? We're seeing what we would expect. It looks like the null hypothesis describes, right, the marijuana users. Their memory doesn't seem to be different from anybody else's. But if we reject, we're saying we have evidence that they are different from everybody else. All right, we're at the end of this. This will be it for 9.2. I will have a couple stats garages posted so you can work through these examples a little bit better.